Okay, welcome back. This is the second lecture about superconductivity, and we have completed the first two topics in the first video. So next is the type 2 superconductors, type 1 and type 2 superconductors. Let's see. See, as I mentioned in the first lecture, the superconductivity may lose beyond a critical magnetic field Hc. Let's see how this field classifies superconductors. See, based on the strength of the critical magnetic field, superconductors are classified as type 1 and type 2 superconductors. Type 1 superconductors lose its superconducting property above the critical magnetic field, which means the zero resistance to electrical currents ceased or stopped at Hc. Let's look this field versus magnetic field versus minus negative magnetization graph, or H versus minus M graph. The perfect diamagnetism stops at Hc, and after Hc it becomes a normal conductor. And these are the properties of type 1 superconductors. The material becomes normal conductor if we increase the magnetic field beyond Hc. Below Tc, they are perfect diamagnetic and exhibit complete Meissner effect. They have only one critical field, that is Hc. At the critical field, the magnetization drops to zero, also known as soft superconductors. Examples are aluminium, lead, indium, etc. Okay, next one is the type 2 superconductor, and this is the H versus minus M graph of type 2 superconductors. In type 2 superconductors, after Hc1, magnetic flux starts to penetrate inside the material, but still up to Hc2, it will show zero resistance to electrical currents. See the graph. Here you can see two critical magnetic fields, Hc1 and Hc2. And if you extend this curve, you may get Hc value also. Okay, Hc value. Here you can see it, and see this dotted line. You can see the Hc value. The properties of type 2 superconductors are they have two critical fields, Hc1 and Hc2. The material is perfect diamagnet below Hc1. At Hc1, the magnetic field lines begin penetrating the material, and mixed state is present in this material. Mixed state means the state between Hc1 and Hc2, because in this state magnetic flux is also present. This magnetic flux are able to penetrate inside this material in between Hc1 and Hc2, and this penetration is in quantized units, and that quanta of magnetic flux is known as vortices. Okay, and the material becomes a normal conductor if we increase the magnetic field beyond Hc2. They are known as hard superconductors, and niobium, tin, niobium, titanium, vanadium, gallium, etc. are examples of type 2 superconductors. Now, how to find the critical magnetic field and transition temperature of a superconducting material? So this equation is the answer. This Hc equal to Hc0 1 minus T square by Tc square. Here Hc0 is the critical field at 0 Kelvin, and you will get the value of Hc at T Kelvin as Hc is equal to Hc0 1 minus T square by Tc square. As you know, the temperature and magnetic field affect superconductivity, and this curve tells you how the critical magnetic field changes with the transition temperature. See, after this curve, the material becomes normal, and inside this curve, this material is superconducting. See, next one is the first theory of superconductivity, this BCS theory. Bardeen, Cooper, Schrieffer are the main backbone of this theory. This is the first microscopic theory of superconductivity, and it successfully explained the effects like zero resistance, Meissner effect, etc. And two principal features of BCS theory are Cooper pairs. Electron pairs are formed, which means electron pairs are formed and propagates throughout the lattice. Cooper pair means is the electron-electron pair. And second one is a Cooper pairs propagate without resistance. These are the two principal features of BCS theory, and let's see what is this Cooper pair and all. See, in this figure you can see this there's a positive lattice, and this red circles are the electrons. Okay, as you know, this electron and electron will never attract each other because they are equal, same charge is always repel. Then how this Cooper pair is formed? Let's examine it. At extreme low temperature, if an electron reaches near to a positive ion lattice, the lattice may distort due to opposite charge attraction. This distortion makes a more positive environment around the negative electron. If a second electron approaches near to the first electron, the second electron feels a positive charge near the first electron. So both these electrons will travel like a pair, and this pair is known as Cooper pair. And Cooper pairs are the reason behind the superconductivity according to BCS theory. And next topic is high temperature superconductors. As you know, the low temperature superconductors usually have transition temperatures below 30 Kelvin and must be cooled using liquid helium in order to achieve superconductivity. Liquid helium's temperature is 4 Kelvin, and this process is very expensive, and high temperature superconductors has been observed with the transition temperatures as high as 134 Kelvin and can be cooled to superconductivity using liquid nitrogen, which is much cheaper and easily accessible as compared to liquid helium, because the liquid nitrogen temperature is 77 Kelvin and it is cheap also. See, in 1986, George Bernoulli and Carl Muller confirmed superconductivity in perovskite structured lanthanum based cuprate oxide materials, and they received 1987 Nobel Prize in Physics for the discovery of high temperature superconductivity. See, these are some of the examples of high temperature superconductors. These all are cuprate superconductors. The transition temperature is given in the brackets. See, actually the chemical substitution in perovskite cuprates push the transition temperatures well beyond 35 Kelvin, which means these materials are giving a high transition temperature due to its chemical substitution. The reason of superconductivity in high temperature superconductors cannot be explained using BCS theory, because BCS theory is a failure to explain this high temperature superconductivity. Several models emerged for explaining high temperature superconductivity, but none of them fully explain the phenomena. Some of them explain some portion, but most of them never, none of them explain these high temperature superconductivity completely. Okay. So we are at end of this chapter now, and this is the second assignment. There are 6 questions, and 5 and 6 are problems. You can use our there is only one equation in this chapter. You can use that equation to solve these problems. Okay, and these all are something like an essay type question. Okay, and write it. Okay, thank you.